Okay, so let's start the last talk of this afternoon session. And we have the Professor Hong Lu from the Center for Joint Quantum Studies of Tianjin University, who will talk about tests and implications of Bosonic heterotic duality. Please welcome.
Okay, thank you. First, I would like to thank the organizers for this opportunity. And this is my first time to be in the BIMSA. It meets all the expectations of the greatest scientific institute that I have ever been to. And I'm actually come from a humbler place, Center for Joint Quantum Studies at Tianjin University. And for those who are interested in visiting and better joining us, then this is our website. The university is currently offering a very, very competitive package to young talented candidates. This competitive should be written in a bold face in a large font. So for those who are interested, can contact us. And today I'm going to propose a duality between the Bosonic string theory and the Heterotic string theory at their respective corners of a modulus space. And it's based on the recent 3 papers. And my collaborator, Ma Liang, is a major collaborator who is involved in all the 3 papers. And he was my graduate student, now a postdoc. And Lu Kaipeng is a first-year graduate student. He did a lot of calculation in the second paper. So my today's talk is rather old-fashioned in a sense. It's a bit like in the 90s when people proposed a number of string dualities in the various corners of the modulus space, largely based on the low energy effective action and with support evidence by the supersymmetry and the BPS states. So I would like to include this web of connections to include the Bosonic string theory as well. Of course, you may immediately raise the question, Bosonic string theory has no supersymmetry, and this seems to, we lose the one big tool, try to convince people with the duality. Hopefully, after this talk, during this talk, I will give you some reasonable kind of evidence that you find that maybe there is a validity between superstring theory and the Bosonic string theory. So first, okay, so this is the outline of the subject. So first, I'm going to review some old works. This is old-fashioned, so this work is a resumption of some work we did more than 20 years ago, where we tried to construct supergravities with Minkowski cross-sphere vacuum. And this is kind of opposite what one nowadays do with ADS-CFT. We are not interested in ADS-CFT. We tried very hard to find a Minkowski cross-sphere instead of ADS cross-sphere. The motivation behind it was to understand the non-abelian gauge symmetry in flat space-time geometrically. So this is a bit of pedagogical. There are 2 important classes of continuous symmetries in the fundamental physics, in modern fundamental physics. One is the coordinate transformation invariance or the diffeomorphism. Another is the gauge symmetry. And the gauge symmetry, both abelian or non-abelian, is mathematically more elegant because the transformation is linear, while the general coordinate transformation is non-linear and it looks rather messy. So you would think that it's easier to understand former than the latter, but the diffeomorphism actually is much easier to understand since we can visualize them. And we cannot visualize scalar spinor fields easily, and it's difficult to understand the origin of the intrinsic symmetries. Of course, I'm sure many people may be able to visualize what's a spinor, what's a scalar. I'm just talking about in my own point of view. The only thing seem to be able to understand is geometry. So I would like to see the geometrization of this intrinsic symmetry, which provide a useful way, at least for me or some of us, to understand their origins. And this work was pioneered, of course, for the abelian gauge symmetries was pioneered by the Cruz and Klein. A special Einstein-Maxwell dilettante theory can be obtained from pure gravity in 5 dimensions. But it's not an Einstein-Maxwell theory because you have a massless dilettante and you cannot truncate out this massless dilettante from the equation motion. And this massless dilettante doesn't seem to exist in our universe. So if we fail to do that in 5-dimensional gravity, what about even higher dimension, pure gravity? It turns out we cannot consistently embed Einstein-Maxwell theory in pure gravity in any high dimensions. The massless scalar modes cannot be all decoupled. So you always have something buy one, get one free kind of thing to get some extra which you don't like. Of course, embedding Einstein-Maxwell theory in M theory or strings is possible and known, but these theories involve high-form gauge symmetries. So if we don't understand quite well what's the Maxwell gauge symmetry, then I find high-form gauge symmetry would be even more difficult. So it would be like using the arcane or more difficult words to explain the simpler words. So a pure geometric origin of U1 gauge theory or Einstein-Maxwell theory does not seem to exist. So what about Yang-Mills? If the internal space is not torus but round sphere like Sn, then its isometry group is SOn plus 1. Now if we apply the Cruz-Klein idea on Sn, then we will get n plus 1 over 2 number of 1 forms, carrying isometry group of SOn plus 1. So this idea was first considered by Pauli before the concept of Yang-Mills field. At I think like 53 or 52, Pauli envisioned a 6-dimensional space-time as a product of Minkowski 4 and 2-sphere. And he would like to find a series like Cruz-Klein theory in 4 dimensions, which would involve the isometry group of the 2-sphere. But his idea did not work out for various reasons. First, Minkowski 4 cross S2 is not a vacuum solution of Einstein gravity in 6 dimensions. Now that problem can be easily solved by adding a cosmology constant. With a suitable cosmology constant, then the theory would admit ADS4 cross S2. However, the reduction then turns out to be not consistent, unlike the Cruz-Klein torus reductions. So this is a demonstration by Mike Duff and Chris Pope in the 85. So we consider Einstein gravity with a cosmology constant. So then this would be in d plus n dimension. So this are the equation motion in d plus n dimensions. Now consider reduction ansatz with all the scalars turned off for simplicities. Just turn on the Yang-Mills fields. So here, y is the internal coordinates of the Sn, and the k are the Killing vectors living on the round sphere. And this would be the ansatz with all the scalars turned off. The Einstein equation, if restrict to the d-dimensional directions, then we'll get these equations. So this is becoming the lower dimensional Einstein equation with kind of effective cosmology constant. Then this will be the source. Looks like the Yang-Mills field, and they are coupled to these Killing vectors. In the case of a torus, then the Killing vector of the product of Killing vector just gave you a delta ij. But for the n sphere killing vectors, this quantity depends on the sphere coordinates. So you have this depends on only the lower dimension, and this also depends on only the lower dimension, while this coefficient depends on the internal coordinate. So these equations are inconsistent. So since miraculous happens in 11-dimensional supergravities, which in addition to the Einstein-Hilbert term, you also have a connect term for the three-form potential. And furthermore, you have to include the FFA term for the purpose of supersymmetry. Yeah. This part, which are the product of like a dot product of the killing vectors on the internal sphere. And these killing vectors depend on the internal coordinate, y, basically. So now you have this depend on only the x coordinates, and these are the x coordinates, and this part depend on y. So the consistency would imply either this and this will be both zero. What? Yes, right. Now the picture changes because you have additional field. Now the equation motion becomes something like this in the 11 dimensions. And now you would have, in the addition contributions from the internal space in the metric part, you would also have contributions from the four-form contributions, such that the energy momentum tensor now you would have additional contributions. So this first part contribution from pure gravity sector, and this is coming from the killing vector. Sorry, yes, okay, sorry, yes, it's killing vectors. You're right. So I hope I was correct here. No, it didn't mention that. Okay, here it's killing vectors. Then the gravity contribution plus the matter contribution, they give precisely this delta Ij. Then this reduced to consistently to the four-dimensional. Right, I think, yeah, the four-dimensional equation motion. Of course, this ultimately leads to Einstein ADS gravity with SO8 Yang-Mills fields in 4 dimensions, or sorry, and SO5 in 7 dimensions. So this was done by DeWitt and Nicolai. Of course, this is a rather simplistic pictures because this discussion does not mean the sphere reduction of 11 dimensions must be consistent, since we only look at the Einstein equation in the new directions. We did not look at other directions of Einstein equation, and we did not look at the equations of the A3 fields. Also, furthermore, we turned off all the scalar fields. And this could be very dangerous because even the S1 Kroot-Kahn reduction theory showed that the scalars are indispensable. So here, to make the scalars all work is very complicated. It took a very long time, probably over decades, to figure all this out. And the upshot is that it is indeed consistent. And in particular, the 1/6 factor in the FFA term is rather crucial plays a crucial role in the consistency of reduction. And we know that 1/6 is required by supersymmetry because ADS cross sphere background does not depend on this 1/6. It's required by supersymmetry. 1/6 also implies the existence of the U-duality group. If you choose a different number, then it will not have this enhanced global symmetry. And also now we find that 1/6 need for the consistent sphere reduction, even though it's not required for the 2 ADS cross sphere vacuum. So we have seen that Yang-Mills can indeed come from a non-Yang-Mills supergravity cell in high dimension by consistent polytype reduction. The lower dimensional series are called gauge supergravities. They play under the vacuum of those are the ADS cross sphere, and they play important roles in ADS-CFT correspondence. And this provides geometric origins of non-abelian symmetries of a lower dimension from high dimensions. However, all the lower dimension appears to have a Minkowski, do not have a Minkowski vacuum, but ADS instead. This is very good for the purpose of doing ADS-CFT, but try to do anything with phenomenology, try to explain. At the beginning, supergravity was used to study our real world, but this kind of vacuum is not suitable. So the question is, can Yang-Mills in flat space also have geometric origins? This was a dream of Pauli. Pauli's dream requires a 6-dimensional series that has a vacuum of Minkowski 4 plus S2. And luckily, such a supergravity theory actually exists, called the Salam-Sesky model, constructed in the 80s. Salam-Sesky model, if you look at the bosonic sector, then this looks very much like n equals 1,1 theory, but actually it's 1,0 theory. It's a 1,0 theory with a gauge the supergravity with this exponential potential. And so the minimum, the 1,0 the supergravity multiplets include the matrix and the self-due tensor. So then you have a anti-self-due tensor multiplet plus a vector multiplet together with this gauge potential. Well, this is not self-due. It have to be split in 2 parts. The self-due part belongs to supergravity multiplet, while the anti-self-due part belongs to the tensor multiplet. Cannot what? Right. Or you can you can have add further math multiplet to enhance to make this. I think this theory itself is still kind of have anomaly problems. So you have to add additional method to remove the anomaly. Right. G in gauge supergravity, G is usually used as a gauge couplings, so which it's now this here it looks like the cosmology constant. Here so it should not be confused with square root G, which is the determinant of the metric. Right? So this G is a coupling. Somehow in supergraph community they tend to use this G as a gauge couplings of the Yang-Mills, where the G square gives you an effective cosmology constant. No, this does not have a Yang-Mills. This is just one vector multiplet, right? But you can add Yang-Mills as additional. I think that's needed for cancel the anomaly. Right. Well, the G basically is a coupling of the fermions to the gauge fields, right? So the gauge fields, I think probably this vector multiplet here. So the scalar potential does not have a fixed point. So we don't have a Minkowski 6 vacuum, but the balance between these things with this, you see these have opposite sign here, so that you can have a fixed point when the space-time is reduced to Minkowski 4 cross 2 sphere, where this 2 form carries this magnetic flux on this 2 sphere. So this then, which this metric, this solution turns out to be symmetric, and this is exactly what Pauli would like to have, Minkowski 4 cross 2 sphere, and this vacuum preserving 1/2 of symmetry. So this actually, the origin of this from the high dimension is not entirely well understood, right? So there is, whether you believe all the supergravity can come from high dimension or not. And this is probably the counterexample. What's my problem? You mean whether it's consistent or? Right, okay. For symmetric expert, this seems to be obvious. Well, you do have counterexamples when you have a supersymmetric vacuum, but not consistent. Right, but supersymmetry typically is a reassuring feature, right? So here basically that it turns out that one can have consistent Pauli reductions and applying the theory in 4 dimensions n equal to 1 Einstein Yang-Mills gravity with complex scalar. So this is the minimum supergravity. So the gravity multiply just graviton. Everything else matter. So you have one Yang-Mills sector and one complex scalar multiplet. And that was done by Gibbons and Pope. Well, again, it's 20 years ago. So all my sayings is a bit old-fashioned. So this provides the first example of directly realizing Pauli's vision exactly 50 years later. So I find although it's not my work, I find it's rather satisfying to have this result. There's no scaling dimensions. Right, so you don't, this just have one exponential things. So the dilaton will not be fixed, right? It's a running dilaton. They are all, well, I think they are all massless by the construction, but the definition of mass will be a bit complicated in this term. Well, I don't think the G has a dimension of the cosmology, the G square has a dimension of cosmology constant. It's right. Well, I'm glad you have a supergravity expert here. So this is basically is the background of all so you may ask this question, what has anything to do with bosonic string theory or heterotic string theory? Why this would inspire us to think about that? Now you think about that, this in fact is very much looks like a bosonic string theory with some kind of conformal anomalies. So now I'm going to go to the topic I'm going to present, discuss in detail. So we are now consider heterotic string theory, and there is a very intriguing global symmetry. The low energy effect theory of heterotic string theory, of course, is n equal to 1 10-dimensional supergravity coupled to E8 cross E8 or SO 32 Yang-Mills multiply. For our purpose, we should only pick up one vector from the Yang-Mills sector, and that's what we are going. What we have. So this part is a typical string theory, and now we have an additional term here. The inclusion of this, of course, this is n equal to 1 supergravity. The inclusion of this, that means this cannot be any part of the maximum supergravity. The maximum supergravity do not have this term. So this can only be embedded in the heterotic string theory. And the Lagrangian in this, if you look at in the string frame, we know the string frame you have a overall e to the 5 factor, then what's inside basically in the bracket is independent on the Dielectron coupling. All the Dielectron coupling will be overall factor. In this Lagrangian, or in all supergravity Lagrangian, you can have a so-called trombone symmetry. The trombone symmetry is a symmetry at equation motion, but not on the Lagrangian. You basically scale the metric by some constant factor. Then you scale the n forms by this. Then you find it has a kind of homogeneously produced overall scaling of the Lagrangian. So the action or the Lagrangian is not invariant, but because this is a constant, so this is a symmetry at the equation motion. However, in the case of the string theory, before the overall Lagrangian, you also have e to the 5 factor. So this symmetry of the equation motion now can be promoted into the whole action by the shifting of the scalars, so that this becomes the true symmetry. And we can have some kind of generalized kind of Schwarz reduction. Basically, I call semi-gauging the symmetry. Let this lambda to be linearly proportional to the internal direction z, like Krug's-Klein reduction. And this leads to the warped reductions on the internal space z. And because now the z, you no longer, it breaks this constant shifting symmetry, so you do not have a Krug's-Klein vector anymore, because the Krug's-Klein vector is kind of gauging of the constant shifting symmetry of the internal space. So this then will become its reduction index. And turns out that this reduction index is totally consistent, and it leads to a 9-dimensional Lagrangians. And if you look at this Lagrangian, of course, this is 9, but in terms of the structure is very much like the the Bosonic sector of the Slime-Sensky model. So if the Slime-Sensky model can have a Minkowski cross-sphere vacuum, then you would also have a Minkowski cross-sphere vacuum. And also, because of this kind of gauging of these global symmetries, it produces an effective cosmological constant, very much like the exponential scalar potentials of the Slime-Sensky model, but except this is 9-dimensional. Now, the Minkowski cross-sphere vacuum is actually can easily obtained from the non-critical Bosonic string with anomaly term. No, not yet. So here, at the moment, I'm only just consider pure Bosonic sector, and I'm talking about supersymmetry later. So if I consider Bosonic string theory, now if without this conformal anomaly term, what's the difference between n equals 1 supergravity? Add this conformal anomaly term, then it will break the supersymmetry. There's no hope to make this a supersymmetry theory as long as in 10 dimension. Maybe other dimension, I don't know. 10 dimension, this cannot be. So this is the low energy effective action of the Bosonic theory. And the Dielectron, because of this, you cannot have a Minkowski vacuum anymore. but it can be stabilized by the contributions of the three-form flux and this cosmological constant. So this suggests a connection between the bosonic string and warp reduction of heterotic. Assuming that the space-time background had a U1 isometry, that's one typical one is allowed to do in the string theory with the coordinate z, then the bosonic string theory is invariant and the T-duality R over 1 R and also interchange the Krugman-Wani mode. And this T-duality persists even with this conformal anomaly term. But this T-duality had a fixed point when R equal to 1 and the Krugman-Wani modes are equal. So all the bosonic string theory comes in pairs, except at the fixed point. And if you look at the background at the T-duality fixed point, and that is what we have. So the Krugman modes equal to the Wani mode. So usually these two terms will not be same. Also, usually in the reduction, you have two scalars. Now because R goes to 1 over R, so you only have one scalar left. So the reduction is again consistent, and we recover the nine-dimensional Lagrangian, provides that this G is exact same equal to this M in the heterotic reductions. So we have found a duality, at least in the pure bosonic sector, the heterotic string theory 13 was the previous we got with the linear dilaton along the R direction and the non-critical bosonic string theory with anomaly at the T duality fixed point. So these two nine-dimensional Lagrangians are non-equal. So this duality allows to construct new solutions of heterotic theory of the warped that fits this warped reduction from this anomalous string solution with this with this U1 isometry, but keeping the Krugman-Wani modes equal. So just be patient. I'm not talking about the supersymmetry yet, but let me focus on the bosonic sector. So the non-critical bosonic string has M4 cross S3 cross S. It doesn't have a Minkowski 10 because anomaly term, but you can have this vacuum where this H3 takes the flux on these 2-3 spheres. Now S3 is a U1 bundle over S2. So S3 cross S3 have a 2 U1 bundle over S2 cross S2. So one can, this psi and psi theta are the 2 U1 coordinates. One can have a one diagonal combination. So this can be written as a diagonal U1 bundle of T11 space. So we can, then you find that this will be our Krugman modes. This Krugman modes, if you look at here, would give you the Wani mode, and they are precisely equal. So this fits the duality, the condition for our duality map, and this leads to the new heterotic vacuum. And in the string frame, the new heterotic vacuum is simply just Minkowski for cross S3, cross T11 times R. Of course, in the Einstein frame, you would have a warp factor. So the vacuum geometry is Minkowski 4 times R times T11 in the string frame and warped Minkowski R cross T11 in the Einstein frame. Now, so this is a completely new vacuum, and it's not being discussed. People discuss string vacuums for decades, and this, I think, we find these new solutions first, only recently, and you can, without our bosonic heterotic duality, then it's hard to come up with this new heterotic vacuum. You will not even think about doing that. Yes. Well, I don't see ADS5 because this I thought if you want to turn it, then you would have one over low kind of thing, did it? because it's now if this d over z is outside, then yes, indeed you need one exponential. That would be ADS space. But this is the overall Wong fact. I'm happy to have ADS, but unfortunately it's not. I'm not sure. Sometimes I would like ADS, sometimes I don't. Right. I think, well, it must be fibrine solutions of some type, yes. But with a very kind of unusual transverse directions, because it had a T11 space there. And it's not related to this kind of Calabi-Yau kind of, But that we will talk about this with when we talk about supersymmetries. Of course, now the essential question is this vacuum is supersymmetric? If you just get another solution, who cares? You have tons of solutions, heterotic series. So the fermionic sector of the heterotic supergravity consists of gravitino, dilatino, and gaugino, and the corresponding. So these are the Killing spin Suli transformation law and the vanishing of the Suli transformation on the fermions give rise to Killing spin equations. And after careful calculation, we find that Killing spin takes a form. Of course, the Killing spin depends on your view by choice. I don't have the slides. I don't have the slides a bit messy to decide, what would be the view by choice. That would have to go to the detail. Anyway, so this would be the Killing spinors. And the Killing spinor, you have a plus and a minus. So it have three projections. So that means 1/8 of supersymmetry, but both plus and minus are right. So eventually preserving 1/4 of supersymmetry. So it's preserving 1/4 of the 10-dimensional n equal to 1 supersymmetry. That means that Minkowski vacuum is a minimum supersymmetry. So that's the theory. If I can reduce to the 4-dimensional theory, then it will be n equal 1 supergravity with whatever the multiplet. That is, to me, is rather interesting because how we get Minkowski n equal 1 supergravity from heterotic, the usual reduction is on the Calabi-Yau 6-fold, 3-folds, right? And this is totally different embedding with kind of T11 space over this. And it's not Calabi-Yau space. And yet it has the effect of getting a 4-dimensional theory that is minimum supergravity, yes. No, it's not. So I would maybe talk about it later, like. So it has Killing spinors, but is this just luck? Because we motivate these solutions from pure Bosonic background. Minkowski 4 cross S3 cross S3 doesn't have a supersymmetry, and yet map into heterotic theory, then it has supersymmetry. So that is a bit striking. So this relates to another topic I did a long time ago. It's called pseudo-supersymmetry of Bosonic string theory. Bosonic string theory is not supersymmetric, but it has pseudo-supersymmetry in that it admits Killing spinors. It is analogous to the Einstein gravity has Killing spinor equation in general dimension, even though it is not supersymmetric. The consistency, what do you mean we have a Killing spinor? So once you propose a Killing spinor, then you can, these are first order equations, then you can find its consistent condition, integrity conditions. The integrity conditions of Killing spinors should give rise to the Bosonic equation motion. So that's the key point. So whenever you have this kind of consistent set of Killing spinors, I can always add the kinetic terms of the fermion at the quadratic order. Then one can show that the pseudo supersymmetric transformation rules of the whole Lagrange, including both bosonic sector and the fermions, will be invariant, but only up to the quadratic orders. Of course, once you can make it invariant and all quartic orders, then this becomes truly supergravity. Pseudo supergravity is the one that it's invariant at the quadratic order of the fermions. And those are the pseudo supersymmetric transformation rules on the fermions. So the bosonic Lagrange in any dimension, if I add the connect term of the fermions and I propose the transformation rule this, plus of course the bosonic counterparts, then you will find the Lagrange is invariant, but only up to the quadratic order. This is, in fact, is not not any theory can do that. For example, if you consider Einstein gravity with a 3-form gauge potential, like 4-form, then you try to do the similar things. Then you find that you can never construct such kind of theory except in 4 dimensions, except in 11 dimensions, which of course give rise to 11-dimensional supergravity. But what's intriguing is that bosonic string theory, you can do this all the time, right? For all dimensions. Right. Yeah. The true supersymmetry would require the balance of the fermionic degree freedom. That is required for the closure of superalgebra. So what I'm talking about here is that obviously in any dimension you will not be able to balance the things. So the superalgebra will not be closed. So it generates more and more terms. So you will not get finite superalgebras. However, at the quadratic order of fermion, the Lagrange is still invariant. So this still distinguish this theory to other, you don't have these kind of properties. Just you add in, for example, gravity, you would have to have this killing spinner, right? That's then you would say, what kind of fermion would generate this term? Then this would be gravity. No. You just add in by hand. So you don't worry about the balance of the degree of freedom. No. This is just purely gravity theory. Well, maybe it can come, as your questions, I don't know the answer. But I should not say no. I should say I don't know about it. So the killing spinors for the bosonic sector, then you have S3 cross S3. So the killing spinor, you would have psi and psi theta. So that would mean that half of it, you would have half of dependent chi1 and half of dependent chi2. And this would be the complete set of the killing spinor in the bosonic string theory. And then you find the T duality, the bosonic heterotic duality requires that the killing spin should not depend on these directions. So only this direction, so I have to be careful. Only these fermions will be mapped to the heterotic string, say, half of in 10 dimensions. Right. 10 dimensions, then you have U1 isometries. U1 display the law of try to map to the heterotic string theory. So nothing should depend on this. So the killing spinor, these two killing spinor, this part should not go there, and this should go there, and that precisely map to this. So the map of the killing spinors. Those are the killing spinors in the heterotic string theory because you have, so this all in the Einstein frame, you have a walk back there. So while the bosonic string theory, just ordinary Kurzweil reduction, so you don't have that. Right. Then this and this would and picture. Stable against. Well, you won't always say that. Usually, when say BPS solution is stable. Now, in the bosonic sector, these are pseudo BPS. They have killing spin. Is that stable or not? I cannot say. Right. So I'm not sure. But on the other hand, the heterotic side, you would say these are the BPS solutions. Right? So I haven't really analyzed this point yet. So okay, so this is a part of this duality, and any more questions? Then I guess I have to speed up because you become anxious. Right? Yes, right. Okay. Okay, now I'm going to speed up. So now we have in a heterotic string theory, you have a T11 say with a Minkowski cross T11. The T11 have isometric group of SU2 cross SU2. So can I get SU2 cross SU gauge fields from the T11 space? So that we become a Pauli-like reduction, but not on the sphere, but on the T11. The answer is not obvious because type 2, for example, type E supergravities, we have ADS5 cross S5, and this gives rise to consistent reduction. But if you try to replace S5 with T11, then you find that the reduction is not going to be consistent. So this would be not easy going to do, but we can do all the things in the bosonic sector by this duality, because the sphere reduction, three-sphere reduction on the bosonic string series turns out to be all consistent, and so we can do the reductions on the three spheres, where it's very natural to include the SU2 cross SU2 YAMUs into three spheres. So this will be the complete reduction in it, and this is a four-dimensional supergravity with. So this is a bit like the one we saw in the Salam-Sexton model reduced on S2, because now we have an extra piece of the YAMUs field. Yeah, we cannot get that U from here. That will be not natural to get that U1 there. Then we can map this whole S3 cross S3 reduction in the bosonic sector to the consistent reduction of the heteroscale of these T11 reductions. And without this bosonic heteroduality, it will be not going to be easy to think about this kind of reduction energy. It's hard to imagine one would be able to write this, but it works, and it gives rise to the supergravity, and those are the pseudo transformation rules. Everything. Those, yes, right. Those are just standard YAMUs of SU2, right? Two pairs of it, right? Now, this, of course, with this, and we would be able to construct a new kind of supergravity BPS solutions, because from the four-dimensional point of view, if we don't look at the YAMUs part, so this is just like a complex scalar. Then Professor Yao and Vathai et al. Long time ago also constructed this cosmic string, in this theory. And that theory typically one get this from the Calabi-Yau reduction, and now we can get it from a very different type of reductions. So the whole cosmic string solutions can be embedded in a completely different kind of way in a string theories, both in the heterotic string theory, also in the bosonic string theory. In both cases, one can calculate their killing spinors, and it all works. And one can easily see how this set of killing spinor map to the heterotic killing spinors. And furthermore, in 4 dimensions, we see this kind of Bianchi identity, which of course is rather general in the heterotic string series. And Schominger, long time ago, constructed heterotic fibrils supported by this SU2 Tohoku-Yang-Muse. And we can do the similar things starting from 4 dimensions. And of course, in 4 dimensions, the solution would become, I will call that NS minus 1 brane. And it also can be supported by the SU2 Yang-Muse. And compared to here, you may immediately say, what's the big deal? Because you just reduce on this word volume, then you would get the same solution as ours. But that's not quite true, because if you reduce the theory on the word volume, then the supersymmetry wouldn't work, because the reduction on the word volume, the supersymmetry would be all preserved, while our solution basically only have N for one symmetry. And also now you can have a kind of a different Yang-Muse, and you have a kind of multi-instanton solutions. And it's kind of intriguing because in these kind of configurations, when A go to 0, that means you turn off the Yang-Muse. The solution does not really disappear. It becomes kind of fundamental N minus 1 fibril, which had a topology of R cross S3. While if you turn on the Yang-Muse field, then the topology will be R4. So this is what we call that it's a kind of instant moduli and the brane creation. Depends on different kind of instant. For example, the instant moduli also include the 2 instants where coalesce or not. So each time 2 instants coalesce, a fundamental brane would create, while in this process, the total 3-form flux is the constant. So of course, this feature was known for the heterotic string theory, but the origin of this phenomenon is rather mysterious. Now, with this geometrization of this SU2 Yang-Muse symmetry, then the 4-dimension solution can be uplifted to become a solution in the Bosonic string, or further to become a solution of a heterotic string via this duality. And we verify both solutions have killing spinors in their respective series. We thus obtain new type of BPS solution or pseudo BPS solution in either in heterotic or Bosonic string. The brane creation due to the instant moduli cannot, which was mysterious for the heterotic fibril point of view, but with our Bosonic heterotic duality and the consequent T11 reduction, the instant moduli become the parameters of pure classical geometries. Because the A field now is just relate to the isometric group of either T11 or S3 cross S3. So you change of the topology is like turning on the fibers of T11 or S3 cross S3. So everything now can be understood purely geometrically in a classical sense, right? Okay, so I think you said that I should have 5 minutes left, so I do. The work is based on the old motivation of constructing supergravities with Minkowski sphere vacuum, where Yang-Muse fields in flat spacetime can have high dimensional origins, not just ADS spacetime. We propose a Bosonic heterotic string duality, where the heterotic strings with a linear dilaton along the R direction to the Bosonic string theory at the T duality at fixed point. And all these theories are 10-dimensional theories. We obtain this n equal 1 d equal 4 supergravity Minkowski vacuum with SU2 cross SU Yang-Mills multiplet, where the gauge group is originate from the isometry group of internal spaces. The duality maps apply not only to the bosonic sector, but also to the supersymmetry and pseudo-supersymmetry, where at least as a quadratic order of the fermions, everything maps perfectly. We have tested the duality by constructing a variety of new BPS states in heterotic string theory and illustrate how the Killing spinors map to each other in different string theories. The previous to host instanton moduli space and break creation now have a complete geometric origins. So for future work, well, I'm a bit, not entirely clear. We can obviously apply this duality to construct. So far the solution is BPS in both sides, with Killing spin in both sides. We can also construct solution with black objects, so we can study things like the entropies in a different perspective. But to me, more importantly, is this duality serious? So can this duality survive in the high order corrections? I think that is the most important. But of course, like Bush's rule, in string duality is really non-perturbative in the word sheet sense. So this actually, it may not, well, at least it's not that easy for me to work out at this stage. So any suggestion will be welcome. Thank you very much.
Okay, any question? There's a question.
Thanks, Hom. So just going back to my follow-up on the question I asked about this Hull-Strominger system. So I thought any supersymmetric solution of heterotic string theory with four-dimensional Poincare invariance and supersymmetry should be a solution of Hull-Strominger system, no?
So actually, so maybe I will get confused. The Schrödinger Hall solution is, so I was confused with this heterotic fibrate, but obviously that's not the case. So, I'm not entirely sure because this solution involves this linear dilatons in the heterocy. And well, maybe, but one has to go carefully, right? But if somebody claims that they have found the most general solutions, then I can have.
No, so the Hull-Strominger system is the most general, is a sort of set of equations that must be satisfied by any supersymmetric solution with four-dimensional Poincare invariance. And you can, Strominger derived it just using, the supersymmetry variations that you showed. And Hull derived it using the worldsheet sigma model. So if your solution is a solution of heterotic string theory, those properties, it must satisfy that.
Well, the vacuum does have this Minkowski, yes.
Yeah.
Okay.
So I think that might be interesting to explore.
Right. To see they have all of them or part of them can have a bosonic string counterpart.
So yeah, I just mean as explicit solution of Hull-Strominger system, that could be an interesting question in its own right.
I
Because
see. Okay.
in
Well,
general,
thank you very much.
finding explicit such solutions is kind of challenging.
Right. Okay. Right. Thank you. We will look into it. Right.
Okay, any more questions?
Yeah, I saw it usually in as linear electron in the non-critical bosonic string, but are you saying it's in the heterotic string? What is the reason?
You mean why these two series maybe?
Non-critical dimension in bosonic string theory, you need the linear dilaton. Because this.
Well, I mean, all I can say is that in 10 dimensions, bosonic string is not critical. So if I want to say, because I want to relate bosonic string with heterotic string I want to be 10 dimension, that's my focus point. Then I want to say what kind of theory, other theory, then one is a bosonic string. Then I have to add, it's a non-critical theory, so I add a conformal number. Then these two theories are not equivalent completely, only at a certain special point of moduli. For example, the bosonic string theory has to be in the T-duality fixed point. Only that point can be mapped to the heterotic string theory. Not all the heterotic string theory, but only with this linear.
Other questions? No, let's thank the speaker again.